All right, in this video I want to work with you on some of these questions about salts and how the salt pHs can be calculated based on hydrolysis, based on the part of the salt that's going to act effectively as either a base or an acid. So in the last video, hopefully you had a chance to watch it, we explained a little bit about how ions, certain ions, one or the other, in a given salt can be the active one as an acid or as a base. And in fact, in the very last video, we talked about calcium fluoride as a salt. Well, this is sodium fluoride as a salt, and it's very similar in that way. There's going to be typically a hint in these problems that's going to give you some sense of which part of this salt in solution is going to be the effective part. Is it the sodium or the fluoride? Hopefully you know that sodium hydroxide is it's the byproduct or the conjugate acid of a strong base, sodium hydroxide. So that sodium is going to be ineffective as an acid. And the fluoride is coming as the conjugate base of a weak acid. And so it's going to be somewhat effective as a base itself. The fluoride ion will be effective. The hint that we're given, though, as I mentioned here, and they're going to sort of mention this toward the end of the problem a lot of times, they're going to have to give you this information. The Ka value for HF, hydrochloric acid, is 7.2 times 10 to the negative 4. That's going to be the hint that, this fluoride ion from this weak acid is going to be the important part of this particular salt. So a lot of times that hint is going to be there. You'll be able to make the connection that it's the fluoride that's going to be the star of this problem. To do that, we want to understand and be able to come up with the equation that shows fluoride doing that. And we wrote this at the end of the last video, so it's pretty fresh. Here's the fluoride ion, which is the conjugate base of a weak acid. Here it is acting with water. So it's going to react with water. Water is going to undergo hydrolysis when exposed to that conjugate base, and as a result, we're going to see the base particle hydroxide produced, and we're going to see hydrofluoric acid also produced. Here's the equation that shows fluoride acting as a base. If we make OH ions, as you see this equation doing, then we'll get a pH above 7. And so we would expect the pH should be greater than 7. That's our first sort of mental sort of step here to think, man, did I get it right at the end? Did I end up with a pH that's greater than 7? Hopefully I will. It doesn't have to be a lot greater, but at least somewhat greater than 7. If this is the case, if we can recognize that this equation shows the fluoride ion acting as a base, and that's the important one from sodium fluoride, then what we want to do next is sort of go ahead and write ourselves up a rice table. We've got our equation. As with most of our acid-based work, this will be a 1-to-1 to 1-to-1 reaction. So what do we know? Change and equilibrium. Our initial amount of fluoride from this fully soluble sodium fluoride salt in solution. Sodium salts always being fully soluble. Our amount of fluoride available will be 0.30 moles per liter. The sodium is a spectator because it's not effectively acting as an acid itself. We don't have to worry about the sodium, but the fluoride that solution contributes, or that salt contributes to the solution, is the active part. Water, as always, we kind of leave water out because it's not important to our Ka expression or our Kb expressions. And then on the other side, as often is the case, we'll start these out as filled in with zeros. What's going to happen? We're going to lose some of this fluoride as it begins to react in solution. We'll lose some of the fluoride, and the OH and HFs will have to increase. Okay. So this will go up by some x. This will go up by some x. If they're asking us to calculate pH, be thinking ahead, what do I need to do to calculate pH? Well, I can get it as inverse log of hydronium H3O concentration. I don't have H3O being made here since this is a base acting, not an acid, or I can get it via POH, and that looks like what we'll do here because we're going to have a hydroxide concentration right down here at the end. That ion concentration can give us POH, and from that we can easily get pH. So be thinking ahead. That's the number I really need to get to, and of course that number is going to be X as I finish out my rice table. Now, how do we know again that our X over here can be treated as negligible? You can treat it as negligible in nearly every weak acid-based problem, and there's no exception here. In a weak acid-based problem, the amount of X being lost is going to be quite small by comparison to the 0.3 moles per liter that we're taking it away from. So I'm going to go ahead and call this negligible. You can write down negligible, or as I've shown you before, you can write down somehow, mention that X is far, far less than 0.30 molar. So we're gonna go ahead and treat it as negligible. Sorry about my screen being a little touchy this morning. If that's the case, this will be approximately 0.30 at the end as well. Now, why is that important? This is going to be part of our K expression. Now, they gave us the Ka value for HF, the weak acid that gave us the fluoride that's interesting in this problem. But that Ka value itself can't be used directly because we're not talking about the acid behavior of HF in this case. We're talking about the base behavior of its conjugate, right? And so in this case, we're going to need from this HF value, we're going to need a Ka value for HF. We're going to need a Kb value for its conjugate. And hopefully you remember that Ka times Kb for any acid-base conjugate pair, okay, Ka times Kb is 1 times 10 to the negative 14. Just as we've seen 10 to the negative 14 in other places in this unit. So in this case, if I know Ka, I can find Kb from it. Kb will be 10 to the negative 14 over Ka, which was given here as 7.2 times 10 to the negative 4. Sorry, I missed a 1 up here. And if I do that, I get a Kb value for this particular base of 1.4 times 10 to the negative 11. That's the Kb value for fluoride ion, for the fluoride ion as it's reacting according to this equation. And if we think about our Kb expression, Kb is going to be, according to this reaction, our OH concentration times our HF concentration, our products, over our fluoride ion concentration. And water, of course, being left out. Now, what of that do we know? We know most of it. Well, I should say most of it, but we know enough of it to solve. Our Kb value is 1.4 times 10 to the negative 11. We just figured that out over here. Our OH value is x, as is our HF value, x. So on the top I have x squared. And on the bottom I have a fluoride concentration of 0.30. Remember when you're filling in a Kb expression that you want to be sure to use only values from the equilibrium line of your rice table. Those are the values that get plugged into a K expression of any kind. For Q, in other places, we sometimes use the initial concentrations. But in this case, we're looking at an equilibrium constant, so we're going to use the equilibrium concentrations. Now, I won't begrudge you the algebra to work this out. We're going to need to get x squared alone, and then we're going to need to do a square root. So hopefully you can handle that. If you do, pardon me, I better switch back to a pen. X, if we do all that math, right, x will come out to be 2.0 times 10 to the negative 6. Now, what is that? That's x moles per liter. That's the molarity of our OH concentration over here in my table. It's also the molarity of my HF, right? But we don't care as much about that because this is going to give us our pH, right? So to finish this out, if we know that that's our concentration of the hydroxide ion, the pOH we'll calculate here would be inverse log of 2 times 10 to the negative 6. And if I do that, my pOH will be 5.69. Now that's not pH, remember. pH will be 14 minus that 5.69. And that's going to give me a pH of 8.31, and that's the answer that we're looking for in this problem. It asks us for pH, which remember we can come at from the hydronium ion side, or we can come at it sort of a roundabout way from the OH ion concentration, which we had to figure out here since we had the active participation of a base with water in hydrolysis to make that hydroxide concentration. It's telling us that this solution would contain more base particles than acid particles, and that's the case because we have an active base in fluoride, but we lack an active acid because sodium is a spectator, it's a neutral ion in solution, and so the only one contributing to pH in this case is the fluoride ion, which is acting as a base, and we see its pH comes in at 8.31. So figuring out from the salt which participant is the important participant, and then coming up with at some point along the way here its Kb value if it's a base, or its Ka value from the given Ka or Kb for the original acid or base. That's kind of the idea. Let's take a look at another one, number 9. Calculate the pH of a 0.1 molar ammonium chloride solution. And they're giving us a hint. Again, the Kb value for NH3, 1.8 times 10 to the negative 5. That gives me a pretty subtle hint that this NH4, not so subtle hint actually, that this NH4 is going to be the active part of my salt. Now let's think about why. Chloride, remember, is coming from HCl as an acid, and that's a strong acid. So since HCl is a 100% dissociated strong acid, chloride is a 0% effective a base. It's not a base at all. And so chlorine is a spectator ion. Since hydrochloric acid is a strong acid, chloride is simply a spectator in the solution. Just as in the previous question, sodium was a spectator, which means ammonium is the star of this show. It's going to be coming from, they gave us here, it's going to be coming, from a weak base in NH3. It gave us the weak base's Kb value. Let's go ahead and bring down the NH4 and see if we can come up with an equation that shows it acting as an acid. To do that, NH4 acting as an acid would need to, in some way with water, produce hydronium ion. And it's pretty obvious then that H2O can accept a hydrogen from the ammonium ion, and that would make NH4 into NH3. NH4 1 plus ion into ammonia. Notice, as we've seen in two of these problems now, that they give us these K values to start out the problem. That HF in the previous problem showed up here at the back end of that problem as a product. And that kind of helps us to remind us about the base in fluoride and its conjugate acid pair HF. Well, down here, they gave us the Kb value for the base, NH3, and that NH3 shows up again at the end of my equation as well. So it should be there. And it helps us to write these equations if we're not quite confident with it or if we're kind of caught up in the moment. But at this point, we have our equation. We go ahead and write ourselves up a rice table. What do we know? Our ammonium concentration is coming in at 0.10 molar. Water's not going to be a significant part of our thought process, so we'll blank it out. Ammonium chloride, remember, is a completely soluble salt. Since all ammonium salts are 100% soluble, we know it's going to give us an ammonium concentration of 0.1. It's also giving us a 0.1 mole per liter concentration of the chloride ion, but as it's a spectator, it's present but not doing anything as far as we're concerned here. It's not having any effect on the water in terms of its ability to change water's pH. So initially we have no hydronium and no ammonia, but as the reaction takes place, we'll lose some of our ammonium, our weak base, or our weak acid from the salt. We're going to form some of our hydronium, we're going to form some of our NH3, and our bottom line then will be X and X. They want us to calculate pH, and in this case then we're going to be looking at pH coming out of this guy, right? pH is going to be the inverse log of that X there under the hydronium concentration at equilibrium. Over here, as with all our other question and with most every question we'll run into, our loss of X is going to be negligible over here. So this is going to be a negligible loss. X is going to be much, much less than 0.10. Much, much less than 0.10. I forgot to do that in the last question, but we can see even still here on the screen, we made the assumption that X is going to be much, much less than 0.3, and look what it came out to be, 2 times 10 to the negative 6. It's way less. Right? So in the end, we can treat that as negligible, and we'll call this approximately 0.10. So as in the last problem, we've got our equilibrium row filled in. Our calculation is going to look a lot the same, and it's kind of a mirror image of what we did in the last problem, in that we are going to be working with an acid here, an NH4. We know it's an acid because it produces these H3O ions. So we're going to be seeing it acting as an acid, which means we need a Ka value for that acid. And our Ka value is going to come out of our Kb value. As before, Ka times Kb equals 10 to the negative 14. So if we're given our Kb value as we are here, we can say that Ka will be 1 times 10 to the negative 14 over the Kb value, which is given at 1.8 times 10 to the negative 5. So that's from right up here in the given information. And if I do that, my Ka will be 5.6 times 10 to the negative 10. That's the Ka for the acid in this question, which is NH4. Okay? So that's the Ka of NH4. And NH4 specifically as an ion here. With that, we can substitute everything into our K expression, as we did in the last question. Our K expression would be products over reactants. I'll write this one out like in the last one, just so we have one more example in front of us. It's going to be H3O, product, times NH3, product, all over NH4 ammonium ion 1 plus from our equilibrium line of the table. So if we use the data that we've got, 5.6 times 10 to the negative 10. It's very sloppy. I'm going to try that one more time. I don't like to be that messy if I can help it. 5.6 times 10 to the negative 10. That's our Ka value. Our H3O and our NH3 are both X and X, so we'll have X squared. And then the bottom, 0.10. And again, I won't belabor the point of solving for X here and doing all the math with you. Hopefully you can do that. If you want to pause and do it yourself, figure out what your X value is, and hopefully you get the same X as me. Highly recommended that you do that. Hopefully if you do, you'll find your x to be 7.5 times 10 to the negative 6. And remember, according to my rice table, that x is my H3O concentration, right? It's the one that we're going to need here at the end of our boxes, at the end of our rice table, to get pH. That's my H3O concentration. So to get the pH, which is what they're asking for, we've only got one step left, and that's inverse log of that. So pH will be inverse log of 7.5 times 10 to the negative 6. If 10 to the negative 6 is our power of 10, we would expect the pH of between 5 and 6. The pH always comes in 1 unit, within 1 unit of that power of 10, and usually 1 unit smaller in value. So 10 to the negative 6 would give me an inverse log of 5 point something. And so this, if we come out and do the calculation, we get a pH of 5.13. So this is, as we would predict, an acidic solution. Right? We had the conjugate of a strong acid, and we had the conjugate of a weak base, which means we should have an acidic salt solution. And the salt actor is the ammonium, according to the equation that we've got, producing hydronium ions by hydrolysis with water. And we have H3Os, but we don't have any OHs being made because chloride can't do that. And so we should have an acidic contributor, but no basic contributor. And because of that, we have a pH on the acidic end of the spectrum, less than 7. Thumbs up, that's what we've got, 5.13. Let's do one more, and then we'll call this video good. So on number 10, we've got aluminum chloride. And again, this is that aluminum ion that we kind of alluded to in the last video, if you've watched that one, showing how aluminum is going to behave here as the acidic contributor to the solution. They gave us the Ka value for that ion straight out of the gate. So that's actually going to save us a little bit of trouble. But let's take a look at this and make sure we understand why. Again, like in the last problem, we have chloride. So this chloride, coming from a strong acid, HCl, is going to be ineffective as a base. 100% strong acid, its base is ineffective. This aluminum, coming from aluminum hydroxide, as a base, would be a weak base. So this is a weak base. This is a strong acid. We should expect that this would be an acidic salt. If that's the case, we should be able to write an equation that shows the aluminum in some way acting in an acidic way with water. And so that gets back to that complex equation with a complex in it, with aluminum hydroxide, or rather aluminum hydrated, as they gave us up here at the top. So this one's a little bit different. So the equation that shows the aluminum acting, okay, isn't just plain aluminum acting. It's actually aluminum, okay, aluminum with 6 waters. Now that's aluminum ion with a 3+ charge surrounded by 6 neutral waters. So aluminum with those 6 waters around it would still have a 3+ charge. That interacting with a water molecule, okay, is going to form H3Os. And as mentioned in that last video, this is something that was talked about in the video from Mr. Faribaugh around 58:46, around 58 minutes and 46 seconds, if you need to revisit on kind of how aluminum with those waters around it is able to take a hydrogen, or rather donate a hydrogen to the water molecule here that's come nearby. How does this water take a hydrogen from that big group? And it's going on, it has a lot to do with Coulomb's law, actually, but it gives away one of the hydrogens to that water takes it. The oxygen in our water molecule here, just to kind of think about it in a little bit different way, the oxygen in our water molecule here has those pairs of electrons that are very accepting sites for a weakly held hydrogen from one of these water molecules in the aluminum water complex over here. And so it ends up taking it. And so let's say that the hydrogen that comes over would kind of bond on right there to that electron pair. That's what gives us the H3O. The other product is the rest of that complex. So the aluminum still has 5 waters attached to it or around it. Plus now, because one of those waters, I'm sorry, not 2, 5, because one of those waters has lost a hydrogen, it's now an OH. But because it lost a proton, a hydrogen proton, that whole group still has a collective 2+ charge. So you can think about it as an aluminum with a 3+ charge, this aluminum here with a 3+ charge, that hasn't changed. And a hydroxide with a 1- charge together giving us this overall 2+ charge. So that's why the equation looks the way that it does. Those waters have no charge of their own, but that ion of aluminum and that ion of hydroxide together then with an overall 2+ charge. Now, we've got our equation. We can see how aluminum in this way is acting as an acid. And so let's go ahead and fill in our rice table. What do I know? Okay. This question says we have a 0.010 molar aluminum chloride solution. So we're going to treat that. It's a chloride. Chloride salts tend to be soluble unless they're with heavy metals. So we're going to treat this as a 0.010 molar solution of aluminum, which has found waters to surround itself with, according to what we talked about earlier there. Water isn't going to be an important part of our conversation, so we'll kind of blank that water row out. Okay. And then, as always, we haven't formed any of these yet. We're going to lose some small x. We're going to gain that small x on the other side of our rice table. Each of these will be x. And as always, we're going to go ahead and treat that x as negligible when it's compared to the 0.010 moles per liter aluminum that's already present. So if we treat this as negligible, far, far less than 0.010, we get an approximate 0.010 moles per liter in our equilibrium line for the aluminum ion. Okay. And to finish this out, they already gave us the Ka value, 1.4 times 10 to the negative 5. Go ahead and fill in my rice table then with that. Ka 1.4 times 10 to the negative 5, given in the problem, is equal to, from our equilibrium concentrations here, x and x on the top, so x squared over 0.010. Take a moment, do the algebra, solve for x. If you believe that you can do that 100% of the time, it's great that you have that confidence. It doesn't hurt to take a moment to do it. But if you do or don't, the answer that you should get in that case is 3.7 times 10 to the negative 4 moles per liter. Now what is that? That is the H3O concentration at the equilibrium point of this reaction is shown. And so that is our H3O molarity. And so pH will simply be inverse log of that amount. Inverse log of 3.7 times 10 to the negative 4. We're expecting, since the hydronium concentration is negative 10 to the negative 4, that we should get a 3-point-something pH. And so we come up here with a 3.43 pH. So not only is aluminum as a metal ion able to act as an acid according to the reaction that we have here, it's quite effective at it. I mean, this is a pretty weak solution, right? 0.010, that's not especially strong. And it's giving us a pH of 3.43, which is a relatively low pH, right? That's far lower than the pH of many common things that we consume and work with on a regular basis. So it's on the stronger end of the weak acid spectrum with a pH of 3.43, even for a fairly diluted concentration of aluminum. So aluminum is actually very effective as an acid. It can be used in various places to lower the pH of solutions in a large way by using an ion like aluminum as available. Sometimes that's appropriate, sometimes it's not. But here's showing how it kind of comes out then as a pH on the acid end of the spectrum. And remember, that makes sense because there's no base contributing the other direction. The chloride, which would be the conjugate base in this salt, from hydrochloric acid, a strong acid, is rendered ineffective by the fact that it comes from a strong acid, so it itself cannot act as a base. Therefore, the only participant here in the solution is the aluminum ion, acting acidically to produce H3Os and giving us a pH less than 7, as we see here. So, hopefully that makes sense. We'll see this in other problems. The next piece of this, and it's going to feel a little bulky, I think, at first, but the idea that we go to next with these is the idea of buffers. And buffers are mixtures of acids and their conjugate base, salt, or bases and their conjugate acid, salt. And in that case, we sort of have to figure out what's the balance, right, of the acid and its conjugate base, or the base and its conjugate acid, and what sort of pH will that give us? When we put those pairs together in solution, we get very effective buffering solutions that can act to neutralize any added acids or bases and keep the pH from changing much at all. But that's what's coming up. That's sort of the next logical step of this as we move on further into problems in this unit. Thanks for listening. I hope this helps out. And I'll post some problems for you to try alongside of these, where you have to come up with similar calculations and determining which part of the salt will be the effective one, either as an acid or a base, like with these. Thanks for listening. We'll see you then.